now let the entire space of events be defined as S. And so we could rewrite probability of B as, see, probability of B intersection S. I'm just going to stop right there if you have any questions, or should I keep going?
No, I think this is all right. I think it's important to just say that this right here is S is the sample space.
The sample space, all events.
So this is this set of all possible events. Okay. And if you can, try to use the thicker part of the marker so that the letters appear thicker.
Okay.
No worries. Okay. So let's keep going.
And let's just say, well, within the sample space, all we have are just B and A.
Okay.
So I could rewrite this as probability of B and A plus the probability of B and A complement. I will use an apostrophe. You can also see us using probably a small letter C. This could also be rewritten as small letter C.
Okay.
Eric, what would you prefer?
Let's use C.
Okay.
For A complement.
Okay, so probability of B and A and probability of B and A complement. Okay, so we can now rewrite Bayes' theorem as probability of just A given B is equal to probability of B given A times probability of A over probability of, so these guys together, I will write this in terms of its conditional probabilities.
Okay.
So that will be, just to check my notes again, probability of B given A over probability of A plus probability of B given A complement over, or sorry, multiplied by probability of A complement.
Mm-hmm. So, right. So we previously had just P of B down here.
Yes.
Right. And so we wrote P of B in terms of P of B union A.
Yep.
And P of B union A complement.
Yep.
And now you've taken it a step further and you've written P of B union A in terms of a conditional probability and a marginal probability.
Yes.
For the two individual terms. Okay.
Yes.
So that's Bayes' theorem right there.
Yes.
Okay.
And we can finally give it a more general idea. So let's say now A is comprised.
Do you want to erase this and we'll get some more room? Okay.
Okay. So
erase whatever you want.
Okay. I will get rid of. So we're gonna finally ignore the sample space. We'll just still assume that A and B are within the sample space. And okay. Finally, so we can kind of write A as a random variable, where A can just take on any sort of, so it could be A1, A2, all the way up to AN. And with Bayes' theorem, probability of A of I given B is equal to probability of B given A of I times probability of A of I over all possible ways is equal to 1 all the way to n, probability of B given A of I to probability of A. So this is the, I would say, a final way of looking at it, or one of the other ways of looking at it.
Right. So before, I think to visualize this, let's say if this rectangle was the sample space.
Yes.
All right. So we can say that this is A right here.
Yes.
And this is A complement.
Yeah.
So now what Arnab is saying is, let's instead think of A partition in multiple ways. So we have one partition here and another partition here. So this is A1, this is A2, this is A3, and this is A4. So in this case, n is equal to 4. Okay.
Yes.
So I think what Arnab has done here is that he's generalized Bayes' theorem to not just the event and the complement, but to any number of partitions of the sample space. Okay, that's a beautiful theorem right there. Okay, so that's Bayes' theorem.
Yes.
So now let's talk about Bayes' theorem in the application of a particular example, shall we?
Let's go ahead.
Okay.